What up, everyone? Welcome back to Structure Free Learning. In this video, we continue our sequence on mechanics of materials and displacement calculations or deflection equations of beam structures. And in this video, we're going to take a simply supported beam with a uniformly distributed load applied only halfway. And what we want to do is find the slope and deflection equations using our singularity function. So to get right to it, the first thing that you need to do is calculate the reactions. And that usually involves drawing a free body diagram and using equilibrium equations. So here I'm just going to use the diagram I have up here, but I know I have an AY, BY, and an AX, which I know is 0 from some of the forces in the horizontal. So let's go ahead real quick and calculate AY and BY. In order to do that, I'm going to take moments about point A, which is essentially BY times 10 meters minus the resultant of the distributed load times the arm. And when I plug and chug, I'll get that this is BY is equal to 3.75 kilonewtons. Next, I want to find the reaction at A, and so the vertical reaction at A, I could either take moments about B or some of the forces in the vertical. So probably most of you will choose to take some of the forces in the vertical equal to 0, positive upwards, minus this resultant, which is 3 times 5, 15 kilonewtons. So I'll get that AY is equal to 11.25 kilonewtons. Now the next thing I want to do is redraw the structure and write out the loading function in terms of singularity using singularity functions. Now when I redraw the structure, I'm not going to draw the boundary conditions in. I'm just going to put the forces, the distributed loads, any external moments, any external things or forces or moments or distributed loading that's acting on my beam. That's what I'm going to draw in. I'm not going to draw any boundary conditions or anything like that. And I also want to draw the coordinate system to remind myself which way is a positive deflection and which way my x-axis is going, or where my origin is. And so here this V, it indicates my deflection. Anytime the beam moves upwards, that's considered a positive deflection, whereas if my beam goes down below the x-axis, it's a negative deflection. Now when we write out the loading function, recall that this displacement function or the deflection equation is equal to the fourth derivative of the loading, which means that if you have a loading function, you can integrate that 4 times to get the displacement or deflection function or the equation of the elastic curve. And at this point right here is x equals 0. This point where the distributed load ends is x is equal to 5 meters. And then here where this concentrated load is, or this reaction, this is x equal to 10 meters. Those are important to note when you write out the singularity functions to describe each of these loads. So let's go ahead and write out that loading function. I'm going to use the symbol W sub x to represent my loading function along the length of the beam in the direction of x. And so here for my concentrated load is described in terms of loading. This concentrated force going upwards, this is 11.25 kilonewtons, the magnitude, times the singularity bracket, x minus the point where it starts, which is here in this case is x equals 0. So x minus 0 to the -1 power. Hopefully you've seen that singularity functions background overview or video to know that this describes a concentrated force in a loading function. Now the distributed load also starts at x equals 0. So here I would have a minus, because my distributed load is going downwards, the magnitude of that distributed load, the uniformly distributed load, 3 kilonewtons per meter, times the singularity brackets x minus 0, and in a loading function the distributed load is to the power of 0. Now when we describe this right here, essentially what we've done is turn on the distributed load at x equals 0, and really what this equation represents is that this distributed load is on for the entire length of the beam. So really what this term describes is a uniform load that is just on continuously for the entire length of the beam. And this doesn't reflect what is actually happening to my beam. So what I got to do is I have to neutralize this portion of the distributed load with another distributed load that goes upwards here, and basically by method of superposition tells me that for this length of the beam my distributed loading is 0. I have to use method or principle of superposition. So I'm going to have another term here. I'm going to add 3 kilonewton per meter x minus, and this is going to start at 5 meters to the 0 power. And then what I have left is this concentrated load at the very end. Here, let me make this a little bit bigger because that looks misleading. There's that 3.75 kilonewtons at the end, and this is a plus 3.75 kilonewtons. X minus, and this is applied at 10 meters to the -1 power. Now another thing to note is that, for this beam here, X will never be greater than 10, so that means this term right here will never come into play in terms of my loading function going from left to right. And it won't come into play with my shear function, my moment function, or my slope function, or my displacement function. So here this term is equal to 0 because X is less than or equal to 10. Seriously, if you can define the loading function, or really probably the more effective way is to define the moment function using singularity functions, if you can understand how to do that, then you're done. That's probably the hardest part in this whole process. But the reality is, like so many other things, and to quote Allen Iverson, it takes practice. We're talking about practice, y'all. Alright, so now that we have the loading function, we're going to integrate once to get the shear function, and that's going to look like this. And here's where you have to remember the rules of integrating these singularity functions. So x minus 0 to the -1, when this power is -1 or -2, you're not going to bring this 1 over n plus 1 down here. There's not this n plus 11.25 divided by n plus 1. That doesn't happen here. So this is just x to the 0 power. And so here, if you plotted the shear function, you would actually get the shear diagram. And same thing here, if I integrate again, now I'm going to get the moment diagram, or the moment function. So here's my moment function, and I want to emphasize here that we started here with the loading function, but really we could have just started from here. We could have described the loading. We could describe what's happening to this beam based on the external forces in terms of the moment function here. And if you again go back to that review or the explanation video for this method of singularity functions, you would see how easy it is to do this. So I'll do another example where I start from the moment function. But the moment function is significant because this is related to the curvature of a beam. And this right here is equal to EI d squared v over dx squared. And I forgot to mention that in this problem here, we're going to assume that EI is constant. So using the moment function, now I can create another function that's related to the slope along the length of the beam by integrating again from the moments. So here, my slope description would be if I include this EI here. So this slope integrating once would be EI dv dx, which is equal to the integral or integrating this moment function, and that would just be, and here I have to add a constant of the integration here. So I'll just add a constant, I'll call that C1. And then again, if I integrate one more time, I will get the deflection equation. This is my slope, and this is my deflection equation. And now what's left is for me to solve for these constants. And the way I solve for these constants is just like in the double integration method, and that is to have boundary conditions. And to do that, you need to remember what the support conditions look like. So if I go back up to the original drawing here, at x equals 0, I have no vertical displacement, and x equals 10 meters, I have no vertical or no deflection in my beam. So what that means is that x equals 0, my deflection v of 0 equals 0, and at x equals 10 meters, my deflection at 10 meters equals 0. And this is where the big benefit is of using singularity functions occurs. If you were to do this problem using the double integration method, you'd have two moment functions. You'd have to integrate that twice, and each moment function would be associated with two unknown constants, and you would need 4 boundary conditions to solve for those 4 constants, which, wow, right? It's just multiplying the amount of work you have to do. In this case here, it's 2 boundary conditions for the 2 constants and done. All right, so here, let's go ahead, let's do the first one. It's pretty easy. Here, the first condition here, we're at x equals 0, the v of 0 equals 0. The displacement is equal to 0, and that just means if I plug and chug EI V of 0, if I look at here, this will be 11.25 kilonewton over 6 times 0 cubed. So that's going to be 0 minus 1/8 times 0. So that's 0 plus 0. Well, x equals 0 is less than this 5 meters. So this singularity function, or this function, doesn't even come into play. It's still 0. So that's 0. And then plus C1 times 0 is 0. Plus C2. And this whole mess is equal to 0. And that just tells me that C2 equals 0. Woohoo! Okay. Next, we're going to put x equals 10 meters in here. And so here, if at EI at 10 meters, this will be, and here, because x is greater than 10, that means this singularity function comes into play. It's turned on, right? It's on over here. And here, that means this 10, it'll be 10 minus 5. So that's going to be 5 meters to the 4th here. Plus C1 times 10 meters. And C2 was 0, and this whole thing is going to be equal to 0. And so C1 here, when you work out the math, it will come out to minus 70.3125 kilonewton meter squared. And here the units are correct, because this C1 is kilonewton meter squared times the length, which give you kilonewton meter cubed, and EI over here has units of kilonewton meter squared. And so when you divide this through, you'll get, for this term, for the displacement, you'll end up with units of meters with the way that we have this equation set up. So last but not least, you just go back and you substitute C1 into here, and you'll have the displacement and the slope equation. So let me write that out for you here. And here are my answers, my deflection equation and my slope equation. Notice the EI is in its proper place now, and the units all work out. So the slope equation comes out with units of radians, or is dimensionless, and you can see that this will give you kilonewton meter squared in the square brackets, and then this EI is kilonewton meter squared, so that'll all cancel out. And this displacement function will end up in units of meters here, the way that we have it written out. All right, hopefully that was helpful, and look out for another example on the method of singularity functions. See ya.